Hi, everyone. Can you hear me? Welcome to this presentation on how real-time Linux accelerates industrial transformation. I'm Edoardo Barbieri, Product Manager at Canonical, and we are the publishers of the Ubuntu operating system. So what I want to cover today, I will start by describing the different domains that play a role in the modern factory. So I will discuss the IT and the OT domains, and then I will move towards how the difference in technologies between IT and OT may be preventing Industry 4.0 solutions from taking place. Then in the third part of the presentation, I will tie real-time Linux and its technologies to the broader market trends that we are seeing, and how real-time Linux helps to accelerate industrial transformation. And then I will conclude with some final remarks. So getting started with the first part of the transformation, the digital transformation through Industry 4.0. So in the history of industry, there have been different prior industrial revolutions. So we tend to count 3 of them. We can go all the way back from the invention of the steam engine in the 1784, and then for the second industrial transformation, when the use of electricity prompted the first assembly line, all the way to the first PLC in the 1969. And what we are facing in these days, in this decade, is the 4th industrial revolution. And it is being driven by increased connectivity, increased networking, and the promise of digitization in manufacturing. And the term Industry 4.0 describes the journey that industrial companies are taking towards a complete value chain transformation and digitization. This is both with their horizontal partners, but also with across their vertical value chains. And in the past few years, many digitization projects were initiated to take advantage of the Industry 4.0 promises, but often they fail to reap the benefits that the industry transformation promised. So to understand why that was the case, we need to go deeper and look at the different domains that play a role in the modern factory. Starting with OT in manufacturing. So operational technology describes the hardware and the software system that tend to execute and control processes on the shop floor. So here we can think of the production lines, the manufacturing systems, all kind of mostly legacy machinery. And this legacy infrastructure tends to pose a barrier between data sharing between devices, but also between two-way communication between devices. The operational technology domain is characterized by a lack of uniformity. Often we have specialized vendors making a specialized device or a specialized component. So the entire OT horizontal layer is optimized by component producers. Each vendor often has got their own production. And because they have their own way of making communication between devices, often they go proprietary. Often the OT layer has proprietary protocols. Usually they went proprietary back in the early 90s, when there were lots of protocols anyway. And because this specialty device only had to talk to another device that the same vendor also made, they figured they didn't have to adopt a broader standard to communicate to their own devices. But today, this is beginning to change because we want to be able to connect our different devices to our manufacturing systems. And the OT layer is also not necessarily resilient or secure. Often, you are unable to provide over-the-air software updates, and you need to install software on your PC for instance, troubleshooting a PLC device. So this is where the OT domain is. At almost the opposite end of the compute spectrum, we have information technology. We have IT at the opposite end in terms of technological advances. And here I'm thinking of the standard networking, the standard PCs that we have in the office environment. This is called information technology because it is designed to send information from one person, from one machine, from one device to another. Communication is part of the IT world. Security is part of the IT world. And this is very different than the OT domain. Even in terms of how it is organized, often the IT function in a company sits with the top-level IT officer, which is very different than the OT domain. It is often organized locally at the plant level. In terms of the standardization aspect, the IT and OT domains also differ quite a bit. We used to have different protocols in the IT layer. We had TCP/IP, we had IPX, SPX, but over the years, we tended to standardize on the single TCP/IP network, so that we expect a certain transferability of knowledge. If you learn how to do TCP/IP on one person's network, on one person's machine, you can then reuse the knowledge to go to your colleague machine. Different technology, but it's still the same network behind. So the IT networks tend to be fairly resilient and standardized. And this is where we currently are. This is the status quo, where we have these two domains, and IT and OT, that have very different levels of technological advances. And on the one hand, we have secure application orchestration paradigms. We have every device being software-defined. We have devices being app-enabled, meaning you can install different applications on your device. And as a consequence, the intelligence of the device is a function of the software it is running. The IT world also saw the over-the-air software updates. On the other hand, in the IT layer, the modern factories, they still require costly manual interventions by field engineers that need to go down at the shop floor to fix a broken device. And these two domains, both OT and IT, they play a role in the modern factories of today. They play a role at the different levels of the modern factory, from the shop floor at the bottom all the way up to the control level, where we tend to have supervisory planning and management. And this difference between the technological advances and the different layers in the automation pyramid gave rise to the name automation pyramid in the modern factory. And the Industry 4.0 concept, the promises of the digitization and the increased intelligence in the modern factories, is not taking place, or it is being slowed down because of the firewall between IT and OT domains. It's almost as if the IT world is living in 2023, is living in the present days, and the OT layer is still living in the 1980s. When we compare modern IT solutions, you can think of app stores, speech recognition, modern programming languages. When we compare all of those advances with where the OT layer is, we see a difference and a lack of technologies, with the IT layer being much more ahead than the counterpart OT. But this security, this lack of connection, the lack of transferability in the OT world is not feasible anymore going into the future. This needs to change because we want to be able to connect all of our systems, all of our equipment to our devices, to be able to keep control of what is happening in the modern factories. The convergence is calling for a transition from closed standards and closed interfaces toward the increased adoption of open standards and open source software with Linux. And this is where we see Linux in real time playing a role. So in the market, we are seeing a big role played by real-time Linux in accelerating the industrial transformation. The industry is adopting software-based functions with Linux on top of it. And the idea is to develop, to update and operate flexibly these functions across all of the different levels of the automation pyramid. This is what gives you the flexibility and the interoperability that end customers often desire. And the industry transformation is going from fixed and proprietary functions toward loosely coupled architectures, often with portable applications and with multi-vendor interoperability. The architecture is loosely coupled because the microservices are portable and they can run on different nodes. And this is where Linux, with the different hardware on which it can run, helps in the transition. So the proprietary platforms of today will be gradually transformed into virtual machines and into microservices. And they will be running over general-purpose compute platforms, the one from the different silicon vendors, delivering the flexibility and scalability that we want. And on those platforms, on those general compute hardware, is where we see demand for real-time Linux. So in the future, all of those technologies that have proven successful in the IT layer, from over-the-air updates to Linux, will be adopted to provide value in the OT world. And Linux is the present and the future of business technologies. We are seeing increased demand of real-time Linux in different functions. Maybe in the past, industrial PCs didn't support real-time compute capabilities, but today we're seeing an increased role playing by that. They were in the past mostly used for HMIs, human-machine interfaces, some data gathering, and today instead we see more demand in industrial PCs for real-time compute capabilities. So Linux and real-time are playing a role in different functions that historically in the modern factory did not necessarily support real-time compute. So some of those historically separate components are coming together. They are coming together in an industrial PC on a single, more consolidated system, on a single form factor with real-time Linux running on top of it. So whether it's an industrial edge server, industrial PCs, or PLCs, robots, or drones, they're all these days requiring real-time compute capabilities. And because of the several applications across a wide range of verticals and use cases, the demand for real-time Linux varies depending on which vertical and which use case you are operating. One of the key market segments is, of course, industrial. This is both for process automation. You can think of petroleum, refineries, but also for discrete automation, like manufacturing and determinism with real-time capabilities in the factory. Also in other verticals, from telecommunications and the telco world, but also in automotive. If you think about the real-time requirements being really tight, if you need to have low latency to prevent a car crash, this is when real-time capabilities come into play in automotive, also for infotainment systems and human-machine interfaces. So there are also several other market applications for real-time Linux, but this is a high-level overview of where we see a role for real-time Linux. So I purposefully wanted to first set the problem statement, explain what are the key use cases for real-time, and how it fits into the broader market trends that we see in industrial. But now, for the final part of the presentation, I want to spend some time on the actual technologies behind real-time Linux and how it works in practice. A disclaimer here is that when talking about real-time systems, we are really looking at an overall system stack. It is not only a single kernel that we are observing. We have to understand the underlying silicon. We need to study the operating system, the networking layer, and the user space applications as well. Each of those layers needs to be optimized to support real-time compute capabilities. When it comes to the Linux context, real-time often denotes a deterministic response time to an external event. And the goal in real-time Linux is to minimize the response time guarantee to those external events and those external stimuli. So a real-time kernel on its own will not necessarily make a system real-time. All the other components of the real-time stack, from the user space applications to the networking, but also the hardware itself, they have to be properly tuned and optimized to take advantage of the real-time capabilities. So the rest of the hardware and the configuration also had to be set up for supporting real-time workloads. This is because even the most efficient RTOS, if there are other latency sinks, it can be very inefficient. So specific tuning is often required, even with a real-time capable kernel. Now, in the next few minutes, I want to spend some time focusing on the operating system layer to understand how real-time Linux in practice works. What are the technologies behind real-time Linux? And to understand this part, it's important to realize that the scheduler of the real-time Linux kernel already has several preemption models, we call them, that are available in mainline Linux to balance the latency versus throughput trade-off. And depending on where you are on that spectrum between latency and throughput, you can be closer to a guaranteed bounded response time, which is what real-time is all about, that we want from a real-time kernel. So for instance, among the different preemption models, server workloads, high-performance computing machines often adopt what we call a non-preemption case. This is the traditional Linux kernel preemption model, and it often maximizes the raw processing power of the machine, irrespective of the scheduling latencies. The more we try to minimize the latency and we try to have a bounded response time, we will have different preemption models. What we call preempt voluntary in the Linux kernel is often intended for usage in your desktop. So if you're running a Linux machine, you can check the preemption model. It will often be preempt voluntary. And this gives a quicker reaction to the different user inputs. The other one I want to mention is called preempt. And this option reduces the latencies of the kernel by making the kernel code that is not executing in critical sections preemptible. So I mentioned the term preemption and being preemptible different times. And now I want to explain what it is all about, because preemption lies at the core of real-time Linux. So what does it mean for an event to be preempted? So kernel preemption in the Linux kernel means that different tasks can be interrupted. It means you can have a low priority process that is running, and when a higher priority process comes around, you can interrupt the low priority one and give higher priority. The CPU will assign its operation to the higher priority process, which will give you the guaranteed bounded response time for your industrial application. So it consists in interrupting the current thread of execution so that a higher priority process can be executed in a timely manner. And increasing what we call the preemptible code surface of the Linux kernel, allowing these capabilities throughout the Linux kernel, is what gives the deterministic response time to an external event. So in this case, it's an example illustration of a kernel without preemption capabilities. In this scenario, we have a hardware device that is running, we have a process that is running, and it raises a hardware interrupt. It requires a service from the Linux kernel. And once this happens, the process will switch from user mode to kernel mode. Only when this process A has completed its request in the kernel, it will then go back to user mode. And at this point, a process switch can take place, and we have process B that will issue a system call and continue with its processing. The issue with this picture is that when a new user space process requests a service from the kernel, if you have a lower priority process that is still running, the kernel will be unable to assign the CPU to the higher priority process, and you will be unable to meet the low latency requirements that your application or that your use case requires. So a kernel without preemption cannot give you a guaranteed bounded response time. At the other end, with no kernel preemption, tasks can't be interrupted once they run. But at the opposite side, we have kernel with preemption capabilities. This is where we allow interrupting the current thread of execution to assign the CPU to a higher priority process. So in this case, making the kernel preemption means that while a process is running, another process can preempt the first one and be allowed to run. And the main characteristic of this kernel is that you can guarantee a deterministic response time because you can always prioritize the different processes that are executing in your kernel. So from the different preemption models that I was discussing before, from the non-preemption model for server workloads, the preempt voluntary model for desktop, and preempt, there's another model called preempt RT. And preempt RT is what takes me to the announcement of real-time Linux in the Ubuntu operating system. So preempt RT is the name of a patch set that is hosted by the Linux Foundation. And those patches are not yet part of the mainline Linux kernel, but they are slowly being mainlined. So those patches implement a priority scheduler and other supporting real-time mechanism to provide the preemption capabilities that I was just explaining 1 second ago. So they are a set of modifications to the Linux kernel to change its scheduler from the default priority-based scheduler to one that is more sensitive to lower latency and will be able to reduce the response time to external events. So those patches are not yet upstream, but have now been integrated in the 22.04 release of the Ubuntu operating system. So the standard Ubuntu operating system that you can use on your server or on your desktop device now supports real-time computing capabilities by integrating the out-of-tree preempt RT patches that give the preemption capability to the Linux kernel. So this is basically all I wanted to discuss today. I wanted to explain the slow transition that we're seeing from closed standards and closed interfaces in industry towards the adoption of open interfaces and open source software. So the proprietary platforms are slowly adopting general purpose compute hardware with real-time Linux often running on top of it. And the real-time capabilities in the Ubuntu operating system is one of the different pillars that will enable the slow transition toward a software-defined Industry 4.0. So this is all I had to cover today. Thank you for your time. If you have any question, you can meet us at the Hall 4 at the booth that is indicated over here. Otherwise, you can also ask me something now for the final 5 minutes. Thank you. So are there any questions? All right. Thank you very much.